Okay, hello. First post-midterm lecture. Cool. So, we finished the whole watch me code a bunch of stuff in Java section. So now we get to move into the next unit of the course, where we're going to be solving a bunch of classic data structure problems. So we'll show you some other data structures like sets and maps and priority queues that are not lists. And then we'll talk about how you implement those data structures to get good performance. And by performance, we're going to use our asymptotics tools from last time to try and measure how good our implementations actually are, so that we can mathematically prove to ourselves, yes, this data structure is very fast, or no, this data structure implementation is slow. So over the course of the next couple weeks, we will throw at you a bunch of different data structures. But the first one you get to see today is the kind of exotic one called disjoint sets. So maybe you haven't seen it before. We'll walk you through it. But the philosophical idea that you'll see today, and it will come up over and over again, is that we will show you an interface. Namely, this is what the users of the disjoint set data structure want to be able to do. So this is the puppet show that the people inside the cave want to see. And then our choice as the implementers, our design of what instance variables do we use for the data structure? How do we actually build the data structure to show the users what they want to see? Our choice of design can have really big influence on how fast the code is. Namely, if we use big theta notation, how fast or how slow the code is as the inputs get large. And our choice will also have a big effect on code complexity. So depending on what we choose, we might have an implementation that's 10 lines of code, or 100 lines of code, or 1,000 lines of code. So we have to make the right decisions as we design this data structure to get something that is fast and hopefully also simple to write. So that's our job today. We're going to show you the data structure. We're going to tell you about what the people in the cave want to see. And then we're going to be the monks, and we're going to choose. Do you want to hold puppets in front of a fire? Do we want to make like little finger horses with our fingers? Like, what are we going to do to show the people the puppet show that they want to see? That's our job for today, for the next few weeks. OK. Can I talk? OK, I'll like hold it super close to my face. OK, so with that philosophy out of the way, now we can talk about the data structure itself, and we can tell you what exactly do the users want to see. So the disjoint sets data structure, the interface that the users want to see, and they don't care how you implement it, is they want these two operations, which is they want the ability to connect two objects, x and y. And they also want to be able to ask the question, are two objects, x and y, connected? And you have to answer true or false. And the tricky thing about this is that the connections can be transitive. So to give you an example, let's say the user says, I want to connect Russia and China. That's great. There's Russia, there's China. I've drawn a line to connect them. And then the user says, you know what? I want to connect Russia and Mongolia. That's the Mongolian flag, apparently. So we'll take Russia, we'll take Mongolia, we'll connect them. And now we can start asking questions like, are China and Mongolia connected? And the tricky thing about this data structure is that even though they are not directly connected, they're connected through Russia, because China is connected to Russia, is connected to Mongolia. So the answer to this is connected question, your data structure needs to be able to keep track of all this stuff and answer true. However, if I ask, or I guess maybe I'm not going to ask a question yet, I will say, let's connect USA and Canada. So there's USA, there's Canada, I connected them. And if I ask, are USA and Mongolia connected? Your data structure must say false, because there's no way to get between the USA and Mongolia based on my current connections. However, I could also change the connections as I go. So I could say, you know what? I'm going to connect Russia and USA, which turns out they're like really close to each other on like the edge of the map or something. So maybe you connect them somehow, and then you ask now, are USA and Mongolia connected? And the answer changes because you added more connections. USA and Mongolia, they are connected now. So now this operation should return true. So that is the data structure that the users want to see. They want to be able to connect stuff and ask you questions about connections. And you have to be able to answer those questions. OK. So turns out this has real world uses. I won't talk about them. You'll see one in homework 2. Any questions about how this whole thing works before we try to actually write code to let the users see this show that they want to see? OK. Anything on Zoom? No? OK. Cool. So I will first make one simplification, and you can think about later that turns out this simplification does not lose any generality. So the data structure works just fine, even if I simplify it a little bit. So the two simplifications I'll make for today, and they won't actually affect functionality, I won't be making the data structure worse, is I will force all the items to be integers. So I'm not going to say, let's connect USA. I'm going to say, let's connect items 0 and 1, or I'll give all the items numbers. And if you want to later, you can store a little mapping that says, oh, 0 was USA and 1 was Mongolia or something. So I will keep everything as numbers just to keep the slides clean. But you can extend the ideas from today to data structures where we are connecting USA or pictures or whatever else you want to connect. The second thing I will do to simplify the data structure is I will force you to tell me about all the objects in advance. So instead of on the previous slide where I started having flags pop out of nowhere, like, oh, here's USA and Canada, and you didn't know they were going to be there, I'm going to tell you in advance there are actually 7 items, 0, 1, 2, 3, 4, 5, 6. So I'll declare to you there are 7 items. When I create this data structure for the first time, all 7 items are disconnected, and then I can start connecting them. So that will be the two simplifications that I'll make. So I'll say there are 7 items, none of them are connected. Let's connect 0 and 1. Okay, there's the connection. Let's connect 1 and 2. Let's connect 0 and 4. Let's connect 3 and 5. And let's ask some questions like, are 2 and 4 connected? Well, there's 2, there's 4. They're part of the same kind of blob of connected things, so the answer is true. But are 3 and 0 connected? Well, there's no connection between 3 and 0, so I say false. But remember, connections can change over time. So I could say, let's connect 4 and 2. Let's connect 4 and 6. Let's connect 3 and 6. Hooray. And now, suddenly, if I ask if 3 and 0 are connected, the answer is now true, because there are some connections that connect 3 and 0 together. OK, so the same thing as the China, USA, Mongolia example, but I made 2 simplifications to make our lives a little bit easier. OK, great. So like we said, this is the interface. This is what the users want to see. And they do not care how you implement it. But we care, because our choice of implementations will determine how easy it is to implement this and also how fast it is. In particular, we have to care about, remember in the asymptotics lecture we said, what we really care about is when n grows really large. So we have to care about, what if a user wants a disjoint sets with millions of items, billions of items? Is our data structure still going to be fast? And what if the user wants to call connect and is connected billions and billions of times? Can my data structure still be fast? So we need to be able to support users who want to do heavy-duty disjoint sets computations. OK. And as we said earlier, the operations can be interspersed. So you cannot assume they're going to connect everything first and then ask you questions. They could ask you some questions, connect some more things, and then ask you more questions. And the answers might change. OK. So let's start digging right in. We'll try and think about what can we do to implement this show for the people in the cave. So here's the very first thing I'm going to think of, which is, well, you and I, we looked at the pictures on the slides, and we were able to answer the questions. Like I showed you this picture, and I said, are 0 and 6 connected? And you looked at the picture, and you said, no, they're not connected. But if I asked you, are 0 and 2 connected? You looked at the picture, and you said, yes. So what if I just told the computer, draw this picture for me? OK, but computers can't really draw pictures. So maybe I'll tell the computer, why don't you record all the lines? So maybe tell the computer, OK, in my data structure, I'm going to write down 0 and 1 are connected, and 1 and 2 are connected, and 2 and 4 are connected. So I'll write down the lines. And then when the user asks if 0 and 2 are connected, I'll somehow iterate through the lines and check if they're connected. So you could do this. But I'm actually going to stop us right there, because this is already getting complicated. Maybe you can already feel the complexity kind of weighing down on us. Because if I have to keep track of all these lines, and then later I have to do some sort of complicated iteration through them and be like, well, 0 is connected to 1, 1's connected to 2, and you have to do all this computation. You can imagine doing this over millions of nodes. This is going to be complicated to write. This is going to be very slow. And I can kind of feel that because I've seen these data structures before. And part of going through these together is hopefully you'll also start seeing when things seem slow and like a bad idea. So we're going to stop right here. We're going to go seek better and more clever implementations. But if you wanted to, you could take this all the way to the end and actually build it. You would just get something complicated and slow because you have to iterate through a bunch of lines, and that's not great. So the next observation, one of several clever things we'll notice, is if I look at this picture and I asked you, are 0 and 6 connected? How were you able to say no so quickly? Oh yeah, we could look at the picture, but somehow, doesn't it feel like 0, 1, 2, and 4 are like kind of part of the same team? And then like 3 and 5 are part of the same team, and then 6 is off by itself? So when I looked at this picture, I could just say, well, 0 is part of this team on the left, 6 is part of this team on the right. They are different, so they're not connected. And the same thing when I asked you, are 0 and 2 connected? You said, well, 0 is part of this group on the left, 2 is part of this group on the left, so yes, they're connected. So maybe if I look at this picture, I see, aha, instead of looking at the individual lines where I said, okay, well, 0 is connected to 1, it's connected to 2, so it's okay. Maybe when you looked at this and you said 0 and 2 are connected, what you really did is you just looked at this big blob over here and you said, oh, 0 and 2, they're part of the same team. There's connections in this team. I don't really care where they are, but they're part of the same group, so they must be connected. So what if I take that idea and I put it in a data structure? So what does that look like? So here's what it might look like, which is instead of writing out all the lines and then using the lines to do some iteration, what if I just kept track of all these teams? So I said at the beginning of the data structure, everybody is on their own separate team. Nothing is connected. And then when I connect 0 and 1, 0 and 1 become part of the same team because they're connected. Do I care how they're connected? Not really, because I only have to answer these true and false questions. No one's going to ask me, how are 2 and 4 connected? They're just going to ask me, are 2 and 4 connected, yes or no? So I'll just put them in the same team and move on with my life. Now I have to connect 1 and 2. And again, I could keep track of the lines, but that's really complicated. So instead, what if I just said 0, 1, and 2? You are now part of the same team. How are they connected? Is it 0 and 2? Is it 0, 1, and 1 and 2? I don't care. All I care is that these 3 items are all connected. What about 0 and 4 connecting? Well, then 4 joins this family, and then 3, 5, and 6 are off by themselves. Then I connect 3 and 5, and I get the picture from before. 0, 1, 2, and 4, part of a team. 3 and 5, part of a separate team. And then 6, all lonely by itself. So now if I ask the question, are 2 and 4 connected? What do? 2 and 4, you are part of the same team, so it must be true. And 3 and 0, you are part of different teams, so you must be false. So this seems a little bit easier to keep track of than the lines from before. I mean, keep going. Okay, 4 and 2 are connected. That one's kind of interesting. It does nothing, because 4 and 2 were already connected. They're already part of the team, so nothing actually changes. What about 4 and 6? Okay, well, now 6 joins the family. And if I connect 3 and 6, now everybody's part of one big team. And if I ask if things are connected, I will get true. Everyone's part of the same team. So that's my better approach. I took the clever realization that I don't have to keep track of lines because I don't care how things are connected. I just care true or false, are they connected? So I can use this idea to hopefully make my code a bit simpler. Okay. That's great. It's a nice idea, but we still have to implement it. So we started with the every single line, not great. Then we thought about, let's just forget about how things are connected, and let's just keep track of groups and teams. So next question for you then is, if I want to actually program this in Java, what instance variables does my disjoint sets object have to have? How do I actually keep track of this thing in memory? Okay, so you can think about it, like, I don't know, 10 seconds. What instance variables would you want to use? You can have like lists, maps, sets, arrays, integers, whatever you want. Strings. How would you keep track of this in a way that's hopefully easy for you to write and also efficient? So one idea that people always like to come up with is, okay, I guess, well, sometimes people say it looks like you have a list of sets, right? There's a set, there's another set, there's another set, and you have a list of them. So a pretty common thing that people like to suggest is, let's represent things as lists of sets. This is what it looks like. So I will say there is a list, and what's each item in the list? It's not a list of dogs, it's not a list of cats, it's a list of sets. Each item in the list, that's one item, it's a set. That's another item, it's a set. That's another item, it's a set. So it makes sense. Just taking what I saw on the slide, putting it in Java. But it turns out this is another danger point where if you make this choice and you lock it in and you start coding things, you're going to have a sad time. It's going to be complicated. It's going to be slow. So here's another point where if you try this decision, and you can, but you would be doomed to failure. So why would you be doomed to failure? Now we have to start bringing back those asymptotic tools from last time to start and measure how slow is this if users want to use this. Yeah, sure, here it's 6 items, so it's not too bad. But what if I was using 1,000,000 items or 1,000,000,000 items? How slow is this thing? So let's look at this case where nothing is connected. I started out with 7 items. They are all part of their own teams. And I ask you the question, are 5 and 6 connected? How do you tell if 5 and 6 are connected? Well, remember, you don't get the pictures. You're just getting this list of sets data structure. So what would Java have to do? What would your code have to do to check if 5 and 6 are connected? Well, I don't know about you, but my code would probably do something like, I'll check the first set. There's no 5. No 5. That's not 5. That's not 5 either. That's not 5 either. Aha, there's the 5. OK, so I found the 5. It's part of this team right here. OK, now I have to find the 6. So I got to go back and, are you 6? Nope. You 6? Nope. 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 There's the 6. OK, which team are you in? You're in this team. 5 was in here. 6 was in here. Are you the same? No. So how did I find 5 and 6? I had to scan through the entire list to find 5 and 6, and then decide that they are not connected. And again, you can imagine this holds true if there are 1,000,000 items, and if some of them are connected, you'd have to scan the entire list to find where the item is, and then scan the entire list to find where the second item is, and then decide that they're not connected. So it turns out this has the overall runtime of theta n. And here I'm using theta n from the asymptotics lecture to say that the order of growth, if I model like runtime as a function of how many things are in my input, here there are 7 things, but there could have been 1,000,000 or 1,000,000,000. The runtime is going to somehow grow linearly with my input. Another way of putting it is if I double the size of my input, it will take twice as long to scan through the array and find, or scan through the list, I guess, and find the items that I'm looking for. If I make my array 10 times as big, then the linear function tells me it'll take me 10 times as long to go through and find the things that I'm looking for. So this already has theta of n runtime. OK. Turns out we can do a lot better. But let's keep track of this in a table just to remind ourselves. So we said that the operations had theta of n runtime. But just to be totally honest and draw a really honest picture, theta of n, that was the worst case. I showed you this really bad case where all the things are separate, and the 5 and the 6, they were at the end. So you had to scan all the way to the end to find the 5 and the 6 and decide that they are not connected. But I don't know, maybe someone gives you a question like, are 0 and 1 connected? That's probably faster. So just to be totally honest, we're going to say theta of n is the worst case, but there might be some other cases that are faster. Maybe someone asks you about 0 and 1, and they're right at the start of the list. That might be faster. So I'll just say big O of n, remembering that big O is like somehow less than or equal to the order of growth. If I model time versus size of the input, or size of the input versus time, if I model that graph, I expect to see a line in the worst case. But maybe there are some cases where the performance is a little bit better. That's why I'll say big O here. But for today, all I have to know is that this is somehow linear time performance. I don't like it. It's slow. It's complicated. I have to write a lot of code. Lists of sets are complicated. And I have to make, or I have big O runtime. So it's slow. So again, just by choosing this Java data structure list of sets, you're doomed to bad performance. So we got to pick something better. OK, so how do we pick something better? So here's the second idea, which is kind of clever. So here, instead of saying, and this is like number 2 of a list of clever ideas that we're showing you today, but as you keep going and developing these yourselves, maybe you'll start seeing these too. So the second clever idea, maybe you spotted it earlier, is let's not have a list of sets. Because a list of sets, we just saw it's complicated, it's slow. What if I instead had an array, and then in my array, because my array has indices, I say in index 0, I'm going to write down the team that item 0 belongs to. And in index 1, I'm going to write down the team that item 1 belongs to. And in index 2, I'll write down the team that item 2 belongs to, and so forth. So what are these numbers representing? Well, if you look, index 0, 1, 2, 4, they all have the same number. Why? Because they are all part of the same team. And index 3 and index 5, you have the same number because you're part of the same team. And index 6, you have a number all by yourself because you're part of a team by yourself. Nobody else has the number 6. So here I'm choosing this implementation where I just have a single array of integers, And if you think about it, array of integers, a lot easier to write than lists of sets. And here, all I have to do is keep track of which team every item is in. And just as a quick note, these numbers, I kind of picked them at random. I could have chosen, for example, to put 9, 9, 9, and 9. Or I could have chosen to put 200, 200, 200, 200. It doesn't really matter. All that I care about is that the numbers are the same, which tells me that they are part of the same group. OK. So that's my next choice. Now I have to think about how fast are the operations. So in this case, how fast is it to tell? And you can try and think, predict if you know the answer. How fast is it? Maybe in terms of asymptotic runtime, maybe just a gut feeling, fast or slow. How fast is it to tell if two items are part of the same set? In other words, to tell me if two items are connected. So if I ask that true or false question, are 0 and 4 connected? How fast is it? Is it linear, where I have to scan the whole array? Is it worse than linear, where I have to iterate and check a bunch of things? Is it faster than linear? Thoughts? Here, I'll do a vote. Who thinks it's linear and I have to scan a bunch of things to find it? Who thinks it's slower than linear? I have to do a bunch of iteration. Who thinks it's faster than linear and I don't even have to scan anything? Oh. So why is it faster than linear? Because if I ask you if 0 and 4 are connected, all I have to do is I have to look up item 0 in the array. You are team 4. And I look up item 4. You are also team 4. You're part of the same group, so you're connected. And how long did that take? I did not have to scan the array. So even if this array had 1 million items, 1 billion items, 2 billion items, it would be the exact same time. I just checked 1, 2 things in the array, and I'm done. So it turns out the isConnected operation is now constant time. It does not grow as a factor of the, how do I say this? It does not grow as the input gets larger. So whether my input is 7 items, or 1 million items, or 1 trillion items, it doesn't matter. The isConnected operation is always constant time. I look, for example, are 3 and 6 connected? 3, you are part of team 5. 6, you are part of team 6. I look at 2 numbers every time. 5 and 6, not part of the same team. You are not connected. And I say false. That's pretty quick. I like that. So we went from linear time, where I had to scan. Is the 5 in here? Is the 5 in here? Is the 5 in here? I went from having to scan all the way through to having this array where I can just immediately pick out 2 items and answer if they're part of the same team. That's pretty cool. So just by changing the underlying data structure, I went from linear time isConnected operations to constant time isConnected operations. So why not stop here? Why is this lecture going on for another half an hour? Well, that's because what about the connect operation? OK. Well, the connect operation, we have a problem. Because what if, let's say I wanted to connect 0 and 5. Well, to connect 0 and 5, I have to take all the items that I have here numbered as team number 4, and I have to take all the items in 5's group. Here I've numbered a team number 5. And I have to make sure they all have the same number, namely that they are all part of the same group. So if I wanted to connect 0 and 5, I would have to take all the people who are in team 4 and change their team number to 5. This way, 0, 1, 2, 4, and 3 and 5, they all have number 5. Right? So this representation would not have 0 and 5 connected. If I wanted to connect 0 and 5, these 2 teams have to unify into one big team. And to do that, I have to take everyone from the first team, 4, 4, 4, 4, and change the number to 5, 5, 5, 5. This way, everyone in this now unified team has number 5. So that's what I'd have to fix. So now, again, question for you is how long, asymptotically, maybe just feeling it out, how fast is it to do this connect operation? Is it constant? Regardless of how big the input is, this will always be fast. Is it linear in the sense that I'm going to have to look at every item in the array? Or in the sense that if my array gets twice as big, then this will take twice as long. Is it worse than linear? Like if I double the input, it gets way, way, way slower. What do we think? OK, I'll go backwards this time. Who thinks it's constant? No matter what happens, I can do this instantly, regardless of how big the array is. Who thinks it's linear? I have to do some sort of scan. OK, anyone think it's slower than linear? Where if I have to do extra iterations, it's even slower. OK, I like linear too. So that's what the people in person said. So I think it's linear because you have to start at 0, 1, 2, And anytime you see a 4, you have to change it to a 5. So I have to be like, are you 4? Oh, you are. Change it to 5. You're 4. Change it to 5. You are also 4. Change it to 5. Okay, you're not 4. You are 4. Change it to 5. Okay, you're not 4. You're not 4. So I have to scan all the way through. And if this array were huge, I'd have to scan all the way through, change all the 4s to 5. So this idea, I call it quick find disjoint sets. Why do I call it quick find? Because finding if two things are connected is quick. All I have to do is look for two things in the array, check if they're equal, part of the same team, yes or no. Super quick, theta of 1. However, if I want to check if two things are connected, look, I have to start at the 0th item and go all the way through the array, and anytime I see a 4, I have to change it to a 5, or whichever teams I am connecting. So I call this quick find because is connected, very, very fast, connect, kind of slow. So I call this quick find. Okay, back to our picture. We had lists of sets ds. That was one idea for how to show the puppet show. That was one of our plans for showing people the disjoint sets show. And that one had slow runtime. Connect was theta, and I had to scan. Is connected, big O of n, sorry, I had to scan. Quick find ds, that was the one we just built with the arrays, and everyone has a team number. Well, that had a very fast is connected operation, theta of 1. But the connect operation required going through the entire array, and that was theta of n. So in my table, I now have two different ways to show people the disjoint sets show to implement the interface. One of them is slow, one of them is a little bit better, but it turns out we can do even better than this, because this one still has kind of a slow connect operation. So I'm going to get this even better using another clever idea, and we'll get a third way to do it. OK, so just to kind of quickly debrief on what we've done so far, we started with lines and boxes. Let's write down the lines, and let's use the lines to compute if things are connected, and we just gave up. That was too complicated. Then we did list of sets. This was slow, even though it was intuitively simple, because now I have to iterate through the sets. Do you have the 6? Do you have the 6? Do you have the 6? That's kind of slow. Then we came up with quick find. Finding things was fast. You're item 2, or you're team 2, you're connected. But if I want to connect everyone in team 2 with everyone with team 3, I have to change all the 2s to 3s, and that's very slow. So let's try to do a little bit better. And this time, instead of throwing out this array idea, I'm actually going to keep it around. I'm going to say, you know what? Keeping these things in an array, I like that because it's simple. In fact, when you implement this in lab, hint, you're implementing this in lab, all you have to do is you just have to write a single integer array. That's kind of nice. However, instead of storing team numbers, which we just saw is slow because you have to change all the 2s to a 3, what if I store something a little bit more radical and different so that instead of changing all the 0s to 3s, so on this slide, they're all team 0, I had to make them all team 3. What if I could figure out a way to store an array of integers keeping track of set membership so that if I want to merge two sets together, I want two teams to unify, it just takes a single value being changed instead of taking 4 or n values being changed. Turns out this is a pretty tricky challenge. You can play with it at home if you want to. Probably live we're not going to have time. But I don't know. Anyone see anything super interesting? I don't know. Right? Because the problem is here, I have to change all the 0s to a 3. So it turns out this one requires another clever trick that maybe you don't see right away, but the more practice we get, maybe you'll start to see it. So the radical different idea is instead of saying everyone is part of a team, namely you're part of team 3 and you're part of team 3, I am actually going to do something a little bit different, which is I'm going to give every item a parent. So instead of saying Zoom, while I do a quick change, listen to myself, tell me how you're going to make this connect operation work. Okay, go. Why not just set this to 2? Why doesn't that work?
Test, 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 test.
I think it's good. Thank you. Okay. Are we back on Zoom? Okay. How much was missed?
It started at 40 and
Okay.
entire introduction slide comparison.
No.
Can you explain it again?
Okay. So I'll explain it. If you heard it, you can think about the question I just posed. So was it this slide that was confusing? Okay, so previous approach in like 1 minute. I said that everybody in the array, the value that you write for the item is the team number that they belong to. So 0, you belong to team number 3, and 1, you belong to team number 3. The new idea for folks on Zoom is that here, instead of saying the team number that you belong to, you assign every item a parent. So you say, instead of 0, or I guess 2, you belong to team 3. You say 2, you belong to item 1. So whichever team item 1 is in, you're part of the same team because you are item 1's subordinate. So if I look in the array, I look up index 2, it says number 1. What does that mean? Doesn't mean you're part of team number 1, doesn't mean you're number 1. It means you're a subordinate of item 1. And then I can look at item 1, and it says, 1, you are a subordinate of 0. And then I look at 0, and the negative number tells me that 0 is the boss. It's the big boss of this team, and the negative 1 tells me 0, you are no subordinate. You are the boss. You don't belong to anybody. And this holds for all the other ones in the array too. So 4, you belong to item 0. So I look up 4, the number 0 tells me 4, you are a subordinate of item 0. And 5, I look it up, you're a subordinate of item 3. And 3, you are no subordinate, you're the boss. So we put a negative 1 there to indicate that. And 6, you're the boss of your own team, there's a negative 1. How do I know that 6 has no subordinates? How do I know that nobody else belongs to 6? I scan through the array, no 6s. So nobody belongs to 6 in this case. Okay, was that sufficient for the Zoom people? Okay, so the question then is, if I have this data structure, how do you make the connect operation work? At this point, I'm just going to have to spoil it for time. Okay, so the first thing we could do, and the first thing that we asked you to try and think about here, is how do you change the array? We have this array of numbers, which is equivalent to this picture you see. How do I change the array, or how do I change the picture in order to connect 5 and 2? I want 3 and 5, this team, and I want the 0, 1, 2, 4 team to be part of the same family. I want them to unify into one big team. So what numbers do I have to change? Keeping in mind that I'm no longer keeping track of team numbers, but I am keeping track of which every item belongs to, or what item every item belongs to. So everyone belongs to another item, or is a subordinate of the other item. So the key idea, I'm running short on time, is why not set ID of 5 to 2? We can try that. We could say ID of 5, you were 3, but I want to connect 5 to 2, so why not just do this? Well, if I do that, I'm saying that 5, instead of belonging to 3, now you belong to 2. So look, 5 belongs to 3, now it belongs to 2, and you get this data structure because 5 now belongs to 2. But this is a problem because look at 3. It has been orphaned all by itself. It's so lonely, and this is not correct. Because remember, if I unify 5 and 2, I want all of these items, including 3, to be part of the same happy family. And if I just connect 5 to 2, that would not be the case. I would leave 3 lonely by itself, and that's too sad, so we can't have that. So instead of setting 5's ID to 2, we need to do something a little bit different, which is we actually need to climb the tree, and we need to say 5. You're not the boss, but your team has a boss. So we climb 5, you belong to 3, 3, you're the boss. And then I do the same thing for 2. I say 2, you're not the boss. 1, you belong to 1. 1, you're not the boss, you belong to 0. 0, you're the boss. So what I'm actually going to do is I'm going to set the root of 5, namely the boss of 5's team, that's 3. Right now, you belong to nobody. Look, 3, -1, you belong to nobody. I'm going to set 3's boss to 2's boss. So 3 used to belong to nobody. Now you are a subordinate of 0. So I change actually the root of 5 to be under the root of 2. See it? See, I'm going back and forth. OK, so that's the idea. Every time you want to connect things, you need to climb the tree. Say, 3's the boss. I climb this tree. 0's the boss. And you both can't be bosses because we're going to unify you. So 0, you're the new true boss, and we'll hang 3, the old boss, under 0. That's the idea. That's how we're going to make connections work. So that's what we did. We made the root of 5 into a subordinate of the root of 2. There were 2 bosses. We can no longer have 2 bosses. So 3, you're one of the bosses. We demote you. You're no longer a boss. You now belong to item 0, who is the true mega boss of this entire set. So how does this work? How fast is it? We need to do the same analysis as before. So at first, it might seem like this seems a little bit faster. Like, how did I connect things? I didn't have to scan the whole array. I just had to climb this tree and climb this tree to find the bosses. However, what if my tree looked like this? So what if, after doing a bunch of connect operations, my tree looked like this? This is a very tall tree. And in this case, how long would it take to connect 2 items? And how long would it take to check if 2 items are connected? So it turns out, if my tree looks like this, the climbing is going to be very slow. Because if I ask you to connect something, I don't know, maybe I have another item 5 floating around somewhere, and I ask you to connect 5 and 4, what would you have to do? You would have to start at 4 and be like, you're not the boss. You belong to 3. You belong to 2. You belong to 1. You belong to 0. Aha, 0 is the boss. So I have to climb this very long tree to find that 0 is the boss, and then hang some other item under 0. So it turns out if I want to connect 2 things, in the worst case, I'd have to climb this very, very long tree. And if I have n items, how long can this tree be? It could be length n if my tree is a very, very long tree like this. So it turns out this is theta n runtime. How about if 2 items are connected? Like, for example, how do I check if 4 and 3 are connected? So maybe if the first one didn't totally make sense, try and wrap your head around this one. How do I check if 4 and 3 are connected? Well, I have to start at 4 and be like, who's the boss of 4? 4. Nope, 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 nope. 0's the boss. Who's the boss of 3? 3. Nope, nope. 0's the boss. So to find out if 2 things are connected, I have to climb the tree twice, see if they have the same boss, and if they do, that's how I know that they're connected. And in the worst case, climbing a very ugly, tall tree like this could take theta n time. Because if I have n items, this tree would have n height, be a very tall tree. OK. So I call this approach quick union. And at first, it seems like quick union is not great, because the connect operation and the is connected operations are both theta of n. And that's because my trees were kind of ugly like this. So the final improvement we have to make is if only we could avoid trees that look tall like this, then maybe we have something on our hands. Because remember on this slide, the tree was kind of short, and things were great. I like when the tree is like this, because here I didn't have to climb a very tall tree. And climbing tall trees is exhausting. But on here, I had a tall tree. So how do I avoid the tall trees to make this work? So I'm going to call this quick union using this tree idea. Now I'm going to add one more approach called weighted quick union. And this is going to finally give us our state-of-the-art data structure. So to do it, I'm going to give you a choice. Do I have time to give you a choice? I'll give you a very, very quick choice, which is, remember, we wanted to connect 2 and 5. And the way to do that, I don't just connect 2 directly to 5. That would orphan 2, or it would orphan the nodes. We don't want that. So instead, if I want to connect 2 and 5, I need to climb all the way to the top of 2 and find 0. You're the boss. I need to climb all the way to 5's boss, which is 3. And I need to say, well, 0 is a boss, 3 is a boss. You can't both be bosses, because we're going to make one big team. So one of you needs to be hung underneath the other. So my question for you is, which do you like better? Do you like taking 3 and making it no longer a boss hang it underneath 0? That's the choice up here. Or do you like taking 0 and saying 0, you're no longer the boss, I'm going to hang you as a subordinate of 3? Which of these do you like better? Which of these do you think gives you better runtime? Who likes the top one where I take 3 and I make it 0 subordinate? You like that. Does anyone like the bottom one where I take 0, make it 3 subordinate? OK, so why did you like the top one? Well, I like it because the tree is less tall. So in this case, the tree ends up being just 1, 2, 3 layers, and we'll make that more explicit in future lectures. Whereas in this bottom one, the tree has 1, 2, 3, 4 layers. The climbing takes a bit longer because the bottom tree is taller. So it turns out the final trick we have to do to actually make a state-of-the-art quick union data structure for disjoint sets is when we hang two trees together, when we want to do this connect operation, you should always take the smaller tree and put it underneath the larger tree. So just like before here, where I took the smaller tree, namely 3, and I made it a subordinate of the larger tree, which was the one anchored at 0, I'm going to keep this rule and do it every single time I want to connect things. So here's another example to make sure that's absolutely crystal clear. I have two groups. This is the group with boss 0. This is the group with boss 6. And the question for you is, if you would like to link 3 and 8, you want to connect 3 and 8, how do you connect it in a way that creates a shorter tree? Don't create the big tree. Create the smaller one. And remember, there are two choices. And remember, you always want to hang the smaller tree underneath the larger tree. So to kind of speed through it a little bit because of our fantastic mic issues, I look, well, do I need to change 3? Remember, no, we don't change 3. We don't change 8. If we do that, we disconnect sections. We don't like that. The nodes get lonely. We don't want nodes to be lonely. So instead, remember, what we do is we need to climb the tree and say 3, your boss is 0. And I climb the tree here, 8, your boss is 6. 0 and 6, you cannot both be bosses. There's too many bosses. We need to merge you. And again, I have to choose. Does 6 become a subordinate of 0, or does 0 become a subordinate of 6? And the rule is, to make our trees short, we're always going to take the smaller tree and hang it underneath the larger tree. So I count. This tree has 4 items. This tree has 6. So we're going to take the 4-item tree and hang it underneath the 6-item tree. That's what I want. So this is the result. I'm going to take 6. You're no longer the boss. You now belong to 0. And now these trees are merged. They become one big team. OK, great. So to implement this, we now have to keep track of size. And one clever way to keep track of size, and you will get to figure this out when you do the lab, is instead of using -1 to represent that you are the boss, you're actually going to use like -4 to represent. The negative represents you're the boss, and the 4 represents that you have 4 people in your team. Or if I put -2, the negative means you're the boss, and the 2 means that there are 2 people in your team. And by adding these extra numbers, this allows me to remind myself, if I want to connect 6 and 0, well, 0 is the smaller one. It's got 2 things in its team. 6 is larger. It's got 4 things in its team. So I need to hang the 0, which is one of the bosses, underneath 6, which is the other boss. So by keeping track of the size of the teams, I can always hang the smaller tree underneath the larger tree. OK. Dang, I'm going to run out of time. Maybe I'll do a little bit of this next time, too. So to quickly finish at least weighted quick union, now we need to think about how fast this is. I guess I'll quickly pause if you have questions. Sorry, this lecture always runs a little bit long. OK. So the key idea, the thing you really have to know to really make this work is whenever you have 2 trees and you want to merge them, you should always take the smaller tree and hang it underneath the larger tree. There are 2 bosses. Which boss gets to stay and be the true ultimate big mega boss? It's the one that had the larger group to begin with. In this case, 0 was had the larger group, so it got to stay as the big ultimate boss. And 6, you had the smaller group, so you had to be merged into the other group. So 6, you're no longer the boss. You hang under 0. And to keep track of how big the teams are, because you're going to have to write this in Java to keep track of how big each team is, when you have an item that's the root, instead of just writing -1 to say you're the boss, you should write -4 to say negative means you're the boss, and 4 means you have 4 items in your team. And then -2 means you're the boss, you have 2 items in your team, and all the positive numbers work like before. So 9, you belong to item 8. 8, you belong to item 6. 6, you're the boss, and you have 4 things in your team. all that's the same. So that's how you might implement it. So I guess the final thing I'll have time for today is how fast is this operation now that I've constrained you to always taking the smaller tree and hanging it underneath the larger tree. So remember, we now take smaller trees, hang them underneath larger trees. It turns out, and this is not going to be obvious at all, but you can go home and play with it a little bit. It turns out that if you enforce this constraint, that the smaller tree must always become the subordinate of the larger tree, that is, if you have two bosses, the weaker boss, the one with fewer items, is going to lose and get merged into the larger one, or the larger group, then it turns out that those ugly trees from before, remember, the whole reason why we're doing this is because this was super annoying. Look at it, it's so gross. It turns out we want to avoid this, and it turns out that if you always hang the smaller tree underneath the larger tree, that is, the smaller boss always loses and becomes a subordinate of the bigger boss, then what you will get is you will never get structures like this. The weighted quick union rule makes this structure impossible, and I encourage you to try it at home to convince yourselves. But I'll show you a quick demo, which is, turns out if you have one item, this is the worst possible structure you can make. If you have two items, this is the worst possible structure. If you have three items, this is the worst possible structure. Or I guess I haven't shown it on the slide. But it turns out if you have three items, you will never get a case where the third item hangs underneath the one. It's just not possible. You can go home, you can try it, play with some connect operations. There will never be a case where you have three items in a chain. And it turns out that the smallest data structure with 4 items looks like this. There's no other way to get 4 items with taller height. It has to look like this. If you don't believe me, go home and try it. Okay. And it turns out that's what it looks like. If I have 4 items, this is the worst case. So it's actually 2 copies of this union together. This is the worst possible case for 4 items. How about 8 items? What's the worst possible case for 8 items? And again, go home, play with it, take 8 items, connect them in any order you want, following the weighted rule. And you'll find out that with 8 items, turns out the worst thing you could do with 8 items, the worst case, is to actually make another copy of this 4-item data structure and union these two. This is the worst possible case for 8 items. And for 16 items, that's the worst possible case, and so forth. So although I haven't proven it to you, and I've encouraged you to go home and try it on your own, turns out that the worst case height, if you use the weighted quick union rule, is log n. How do I know it's log n? Well, one way to do it is to look at the table and say, if this is n, the number of items, and this is the height, and I look for a function where I can put in these numbers and get these numbers, it turns out the correct function is log n. Log of 16 is 4, log of 8 is 3, log of 4 is 2. That's the function that satisfies my pattern. Another way to see it is to note that every time I double the size of the input, the runtime gets slower by 1. So if it's the case that my input doubles and the runtime, the function gets slower by 1, that's logarithmic performance. It's OK if you don't get it. We will do lots more asymptotics, so you do get it. So I guess I will have to finish this next time, unfortunately. But just know that we came up with 4 different ideas for how to show people the data structure of disjoint sets. And the choice of data structure had big effects on how fast and how easy it is to code. OK, I'll see you next time. Sorry for all the technical difficulties. I hope your midterm went well and you had fun. And I'll see you next time, and we'll have more fun. OK, bye.